So the next speaker is Johannes, CEO of Planetary Utilities, a startup company based in California. Another co-founder of the company is Robert Carbon. Many of you know, another very influential figure in model-based systems engineering community. And both of them worked at NASA Jet Propulsion Laboratory in California, and now building their company called Planetary Utilities. So welcome, Johannes.
Somewhere. All right. Hi. Thank you. I'm having an echo here. I need to switch the.
Yeah, at least we can hear well.
Yeah. Okay. Great. You guys can hear me, so let's jump right in. Thanks for the introduction. My name is Johannes, and let me kick the slideshow off here so we have a full screen view. Yeah, so I want to talk today about Starkit, and I call it a design language for space. And really, this goes back to our work at JPL. I'm originally from Germany, University of Stuttgart. We did research on graph-based design languages. That's kind of my research background. And then Robert Carbon was one of the early adopters of MBSE with his work at European Southern Observatory. And then we worked alongside at JPL for almost 10 years. And JPL was one of the places that really got into MBSE early and went all in on it on a broad basis, and had a lot of learning experiences, to put it mildly, during the last 10, 15 years. And so that's kind of the background. And we started out with our company, and our goal is to build a modular space system. We are seeing that with the developments in the new space industry and Starship coming online, there's going to be a new time for space. And the learnings that I saw that limit us really in our progress as a species in deploying more technology in space is really the lack of an architecture that allows for a continuous integration, continuous deployment process for space systems. And so the basis for that is modularity. Much like in the software world, Dockerization has helped a lot, making things more modular. And the system that you're looking at here is a large modular space system. So the individual modules are 1 cubic meter in size, 1 kilowatt in power, 1 ton in mass. So that's just the idea here. It's CubeSats for Starship, basically. And so in the center here, there's a backbone, and that backbone is called Nexus, and it can host these modules. And the specific part about this system is that the modules also contain the subsystems. And so with this design, you can create spacecraft that have more power or less power, that are for Earth observation, that are for lunar missions, that are for manufacturing in space. So you can have all kinds of missions that run on this infrastructure. And that brings us to the second aspect of this is, with this infrastructure, we want to transform space into a marketplace of services. That's really the goal here, that you don't buy a power system anymore, you just buy power the same way that you right now buy power from your utility provider. That also hints a little bit the name of the company. So to build this space infrastructure, we started out with looking at the engineering environment that we need to actually allow this. I want to make one example. The last instrument that I built for the International Space Station was called EMIT. It's a spectrometer instrument. And the time when we unloaded the instrument from the payload bay of the Dragon capsule to the plug-in into the American External Payload Adapter was actually 6 hours because of the robotic arm, which was from Canada. And we didn't have a closer interface. So these 6 hours were actually the driving use case for our thermal system. which sounds kind of stupid. Like you have this instrument that's going to operate for years and years in space on the space station, but you're designing your thermal system because of these 6 hours transfer where your instrument cools out and your electronics are threatened to die. And so that was one of the main learning experiences for me, how a space system, a robotic space system, needs to work. So there's one aspect is you need to be able to get your thermal simulations for all kinds of configurations of your spacecraft, and you need to be able to get them easily and quickly. And so that's one of the design constraints basically for building the system. And then the other thing is like your robotics, you need to be able to access them and actually use them so that the engineers can really grasp and try out things on a digital twin before they engineer their system or while they engineer their system. And so these were all these drivers for building the system. And we saw there's nothing on the market that can do that. And that's why we're talking about software today. Here is an example for one of the space systems that we can now build with this modular system. Let me skip one slide ahead here. A lunar transporter example where you have 3 of the backbones, 4 power subsystems that gives you 100 kilowatts of power. If you now plug in a 4-Newton electric thruster, you can get to the moon in 1.5 years, which is a little bit a long time, right? But you have to look at the payload ratio. So the total spacecraft mass is 40 tons here, but 20 tons of that is payload. And so this will be the cheapest way in a reasonable time to get to the moon. And so this is really showing the advantages of this kind of modular system. If you want to go fast, maybe you take Starship, maybe you take maybe you take a chemical propulsion module. But if you want to go slow, you reconfigure your spacecraft and you go with electric propulsion. So that's just one example out of many that come out of the system. But let me jump around a little bit here. Yeah, so we were basically designing the system and looking at industry and looking for customers. And then we realized we're a little bit too early and we can't really sell this. So we had this prototype of the backbone and the modules, and we had it at a conference and showed it to people, and people were looking at it and were like, oh, wow, like I get it. And some people really said, I always thought space systems should look like that. So that was very encouraging. But the market was not there yet in terms of Starship isn't ready yet. And the space industry currently sees like a satellite the size of one of these modules. So we're just not quite there yet. And then in January of this year, we had also a fire in Altadena, my hometown. Our company was startup early days, so we were working out of my home. And so our town burned down and my house burned down. This is actually Robert and I standing in front of it. But the day before the fire, we actually set up our prototype outside of my garage. It was all stored in the garage for like half a year. And it ended up being the only thing that survived, basically, out of all the things in my house. And this really encouraged us to keep going and to see this concept through, because it was a very strong symbol. And so we moved this prototype to our new headquarters, which is in Monrovia, also in the Los Angeles area. And it's there now in the entry of our warehouse and office. So let's jump over now to the software. So to build this system, we took all the learnings that we had from that time at JPL, and we jumped in and we were like, okay, we want to have something that's enterprise ready and deployable on a large user base. And so we knew that SysML, or we discovered over the time as we engineered the architecture, that SysML v2 is a really good fit for this platform. And so the way we see it is that SysML v2 really can become a platform technology, and that's really new. And I think, as Marcel has mentioned it, there were previous attempts, and a lot of people have built these large integrations. And yet, even if you integrate 20 tools, large companies have hundreds and thousands of tools, right? And the world is such a big place. We can only create these integrations if we have a platform technology that's open, that's permissive, and that really allows everybody to contribute and to use it. And so that's what we see in SysML v2. And that's where our work together with Sensemetry is also very key, because They deliver the core engine. And another core piece for us is OpenMBE. So OpenMBE is the project that came out of JPL. It's all the source code that JPL, all the code that JPL wrote with their model management system. And Flexo is actually the fifth iteration of this model management system. So the naming of these versions is by robots from Futurama. And Execubot was the fourth one for SysML v1, and Flexo is the fifth one. So we'll have fun seeing what kind of names come out of OpenMB in the future. And the third piece in the puzzle here is Tom Sawyer's SysML v2 viewer that we're also using in that application. But on top of that is Starforge, and that's really the framework that we're building around here. Is how do we architect these SysML models so that we get this flexibility and all that functionality that we want to have out of it? And one of the main learnings of that is the Dragon architecture. There's a paper from Robert and the team at JPL that you can download. And it's basically this idea to have continuously evolving but fully representative digital twins over all stages of the life cycle. And so there's this fractional idea that it grows basically as you go down the V, you grow in detail, but it's always a full model. So you always have a model of your control system and a model of your system under control, and you can close that loop in a way. So that's one of the core concepts here, really, for these digital
Johannes,
threads.
Yes. So it would be great if you could think about how to wrap up. We have
Okay. Sorry. Yeah. Let me jump in the last few slides here to show you a little bit, or actually, I want to just show you, if I can take like 1 more minute. I just want to show you how it is to build space system with Starforge. So I'm saying create a new nexus, which is our backbone. And so what I'm getting here is a 3D model, a lightweight 3D model of the nexus. And then I can say add a thermal unit, please. Always be friendly to AI. And then I say add a power unit. So that's kind of really just to show you how we want to interact with this system and this architecture, is that we have this chat agent, and then we can use that to interact with the model of the system. And we can build up the model, but we can also interact with the model itself. So we can, for instance, say, please deploy the radiator. And I think this is really crucial, is that we can now bring functionality with these new containers basically to the spacecraft, but then with the same interface, we can also interact with this new functionality and use the API basically of these containers. So yeah, I think that's pretty much it for the vision behind Starforge. And maybe we have time for one question, or if you want to go on, go on. Thank you.
Yeah, thanks so much, Johannes. So